Bristronica 2025. We are with Dimitri for Emute Lab instruments. And what do you have this year for us?
Hi, so we are demoing two modules. The first one is our first module that was released just over a year ago here at Bristronica, and it's called uSEQ, and it's what I like to call a live coding CV and gate sequencer and processor.
All right.
So that's a bit of a mouthful. Let's unpack it. Live coding is a practice that's been going on for decades now, and it's not specific to modular or hardware in any way, but it involves using code as a primary interface for making music and visuals live in front of an audience, and you're interacting with the code as the performance is happening, and changing the code changes the music that is produced. And so I've been doing live coding for a few years now, and I really wanted to be able to use some of what I've been coding with my modular synth. The problem was that to do that, you need what's called a DC-coupled audio interface if you want to do like sequences and LFOs and various sorts of like control rate CV. And so that was limited by the amount of outputs that the audio interface had, and also I needed to have my laptop with me to produce those signals so that they could then be sent into the modular. The voltage ranges weren't exactly what I wanted them to be, so we were thinking, like, isn't there a better way to combine live coding and Eurorack modular synthesis? And so what we tried to do is, instead of having the computer generate all the signals and then pass them to the modular through an audio interface, instead we put the computer inside the module. So the module itself has a Raspberry Pi Pico chip. It's all open source, by the way, hardware, software, and the editor that we're using. So it's this module right here, yeah. And it has 3 CV outputs here on the left, A1, A2, and A3, and 3 gate outputs on the right, D1, D2, and D3, and 2 CV inputs, 2 gate inputs. And so these can be used to control some parts of the code using other modules. So for example, if you have a controller like the Gliss, or I have an XY joystick at home, I like to use that to change patterns. And so an important thing to note is that the module doesn't do audio. So it doesn't generate audio and it doesn't process audio. It works on control rates. And that's for 2 reasons. One of them is practical, because we're using an affordable microcontroller chip. And on top of that, we are dynamically interpreting a high-level programming language. So there's a lot of overhead, and there's only so much that you can get out of such a chip. But then we decided that it's a great idea to lean into that. Because there's a lot of programmable modules out there already. You can make them into a reverb, you can make them into a delay or an oscillator. And the problem with that, at least that I've had in the past, is that if a module can be anything, then I don't really know how I want to use it, and I keep changing what firmware is on it, and it keeps feeling like it doesn't belong in my patch. Whereas this, I only ever use as a sequencer and CV generator, and so I've built up a collection of patches that I like to use with it, and I find that it works great. So let me give you a little demo.
But wait, it's connected to the computer.
Yeah,
via
so it's connected
USB-C?
via a single USB-C cable. It doesn't need to be a computer. It can be any device that can send text to the module over USB serial. So we've used mobile phones and tablets in the past. But I like to use this editor on the computer. And the editor, by the way, just runs as a web browser app. And so you don't even need to install it. You can go to our website, which is useq.emutelabinstruments.co.uk, and the editor will load straight up. And so we're connected to the module. If I turn the patch up a little bit, we've got a simple patch going where almost all of the modulation is coming from uSEQ itself, and we just have one drum voice going into one filter and then into a reverb. And so if I unplug the module, it just keeps working exactly the same way as before. So all of the code is running on the module. It can be saved on the onboard memory, and then you can power down, go to a gig or to a jam, and it will keep working exactly the same way as it was before. But I like to have the editor up and running connected to it. And so just to give you a little bit of an overview of what we're seeing here, the editor is visualizing the signals that are being produced by the module, and everything to the right half of the screen are the future signals as they're coming. So this is the current signals that are being played, and then this is all a preview of what's about to come. And so each one...
The playhead is at the very center.
Exactly, yes. This is the player head in the middle here. And so 0 at the bottom is the lowest possible voltage that you can get out of the output, so -5 in our case. 0.5 is 0 volts, and 1 is the highest voltage, which is 5 volts. So -5 to 5 for the CV outputs. And so each one of these expressions corresponds to one of the outputs of the module itself. So I can, for example, D2 is digital output 2, it's my second gate output, and it's currently playing a Euclidean sequence that is the result of adding together 2 Euclidean sequences.
Which language is that?
So this is a language that we've developed ourselves. It's called Modulism. And it's an open source language specifically for making time-varying signals that work well with the whole ethos of Eurorack and how everything is controlled. And it's a language that's based on a language called Lisp, which is an almost historic, at this point, programming language that came out in the late 50s or thereabouts. And so the language and the firmware are open source, and we're open to the idea of in the future having different languages running on the module as well. And so just to give you an example of like how a pattern like this can be read. So if I for a moment turn off all the other visualizations, we can focus on the gate outputs. I just need to find all of those. So the gate output in the middle is what's triggering the drum voice in this particular case. And so what it's doing is it's adding together 2 Euclidean sequences, each of which is looping through all of its steps every bar. And in the first Euclidean sequence, if I isolate it a little bit, we can see that the number of active steps we're actually sequencing to be either 6, 11, 7, or 13. These are just the numbers that I liked the sound of. And we're going through these numbers every 2 bars. And so the entire sequence can then be passed into these special functions called slow and fast. And so we can slow down the gate pattern, or if we really want to go crazy, we can speed it up. And then to give you some examples of the CV outputs, so CV output 1 is adding together 3 signals. So it's adding together a sine wave that is being multiplied by a small number just to keep it quite small. Another sine wave which has a frequency of every 2 beats. It loops, twice a beat. And then finally, a bar is just a phasor that goes from 0 to 1 every bar. So if I remove all of these, the sine waves, for example, then we just get a bar phasor. This is tied to the built-in BPM of the module, which can be set using a set BPM function. So we can set it to 140, for example.
So of course you can save bits of code.
Yeah, exactly. So you can have many bits of code that relate to the same output. Only the last one that you've evaluated is the active one. So if I scroll further down, I have bits of code from previous performances or previous demos, and these are there as like it's kind of like my workspace. Sometimes I go back to them, and sometimes I change them, and of course you can save them and load them from your hard drive as well.
You can save them on a text file.
Yeah, exactly. So with these buttons up here, you can save and load them to text files, and then we're building a library of patches that we are uploading, but also contributions by various users. And so the idea is that if you don't want to live code it, or if you're kind of trying to get started in live coding, you don't really have to get down and dirty with the code straight away. You can just find some snippets. There is a built-in help guide and documentation. So there's a user guide that talks about different aspects of the module. And then there's a built-in function reference with different tags to filter the function. So for example, if I go into all the sequencing functions, we see Euclidean function generator. We have functions that produce gates with various step widths, and so on. And so each one of these will have some examples that you can copy paste and get started straight away. So let's in fact do just that. I can copy one of these examples, and then we can get rid of everything else, and we can paste that example. And so suddenly we're listening to a much more stable.
Is the interface telling you when your syntax is wrong?
Yes, so this is, it will tell you when there is something wrong with the syntax. It's not always clear or possible to know exactly what's wrong, so we're working on trying to make it as user-friendly as possible. But if, for example, you have missed the parenthesis somewhere or the name of a function is wrong, it will underline that and kind of try and help you as much as possible. And so, just to give you an example, we can have a sequence here. I really like using these LED cables because they can kind of visualize all the different patterns that go on and off. And so one of the things that I think is very powerful about this is that everything that we see on the screen, every number, every function, everything can itself be something that changes over time. So very much like in Eurorack, every single patch point, you can put a signal that modulates that over time. We can do the same in the code directly. So instead of always having 7 active steps in our sequence here, and let me zoom in a little bit to make that clear, I can say that I actually want to sequence a list of, let's say, 7, 10 and 11 steps, and I want to go through this list every bar or every 2 bars. And so if I evaluate that, then now every 2 bars we're changing the active number of steps in our sequence. And we can do something similar with our CV. So for example, if I want my first analog output to play 0.5, remember is 0 volts, and then -5 volts, and then let's say 5 volts, and then if we go through these values every bar, then what we get is a sequence of these steps. And now where it gets really interesting is when we start combining these things together. So on top of this sequence, I'm going to add a little sine wave. And U sine just means unipolar sine wave. It just goes between 0 and 1. And that can move every beat. And if I run it like that, then we see that the sine wave is way too big because it travels the whole range of CV. So instead, let's just multiply it with a small number that's less than 1. And what that's going to do is shrink it down. And so now we have a sequence of fixed voltages, and on top of that, we're adding a little bit of a wobble. And so we can speed it up a little bit, and then we can make it even smaller, so let's say 0.5. And what I like to do is, let's say, multiply the whole thing with the bar phasor. So what this will do is at the beginning of the bar, this will be 0, and so the whole sine wave will be 0. But then as we're going up the bar, you'll see that it starts fading in that modulation. And in fact, if I slow that down a little bit, we'll see that the modulation starts very low, and then it starts increasing in amplitude. And we can make that even more dramatic if I do something like this. So we can get quite complex waves quite quickly just by adding together sine waves and square waves and multiplying them and doing all of those things that frankly is what we do in Eurorack anyway. We put things in VCAs, we add offsets to them, we attenuate them. And so we build complexity using small components. And so this is just the beginning of an open source platform where the idea is to explore this coexistence of computational music performance and also hands-on control. So we have a few hardware buttons and encoders on the module itself. Those can be read in the code and used to change the speed of the pattern or change the pattern altogether. So you can set it up at home so that you have one pattern on the left, a different one in the middle, and a different one on the right, and save that on the onboard memory. And then you don't even need a computer.
Would you be actually able to plug it on a phone, like with USB-C, and do this on the phone?
Yeah, so there is, technically it works. There is a user interface challenge there, which is what's the best way to edit code on a phone. And actually this is a great segue to something that I've been working on recently, and it's in a very experimental stage, but I can show you a little bit of it, which is to interface with the code. Let's use the gates function. So gates can take a number of zeros and ones and then play those as a pattern. And so I've been adding some experimental support for changing the code with, in this case, a gamepad. And so we can navigate around the code and I can use. I need to hold this because the cable connection is not very stable at the moment with this gamepad. But if I press these buttons, I can change the actual numbers, and then as soon as I press start, it will reevaluate that expression.
Yeah.
And so this is kind of pointing towards the direction that we want to head with this, which is that instead of actually having to type all the code, we want to be able to use things like controllers or joysticks, or even if you have like a controller module, an XY pad and something like that, all of these can be read by the inputs or by the editor itself and used to change parts of the code. And so my goal for this is to be able to get to the point where I can do an entire set without having to touch my keyboard at all. So I can leave my laptop at home, have a little screen on top of my modular rack, and then use a gamepad or a joystick to move around the code and change anything to anything else. That will also make it a lot easier to work with the code on smaller touchscreens, so phones and tablets. But yeah, it's all very possible, and all you need is just a USB serial connection, because the only thing that actually goes to the module is the text.
Yeah.
So as long as we can send the right text, it doesn't. The interface doesn't even have to look like an editor at all. You could have, let's say, a VST with a certain panel and a visual interface, and as long as that can put together the right codes to send to the module, then you can make any sort of interface for it on top of that. So,
excellent. Very interesting stuff.
So this is, on the right, you can see uSEQ's little sibling, which is still a prototype, but we are hoping to release it soon, which is an 8 CV out expander.
Okay.
So it's basically the exact same hardware. It brings its own chip, so you can keep adding as many of these and you don't lose any performance.
How are they connected? Is it I2C? Or?
Yeah, so they're connected via I2C in the back, and I only need to be connected physically to the main one, and then that will send the code that needs to go to the expander.
Excellent.
There. And each one is running its own code.
Very cool stuff. What is, I don't remember, you told me if it's shipping already?
Yeah, so it's been out for a bit over a year now. It's available both as an assembled module and as a DIY kit. And assembled modules are available in Europe, North America, and I believe also in Asia. And the DIY kits are available from Thonk in the UK.
All right.
And they also ship internationally. But also, if people are DIYing clients, they can download the hardware files, they can print their own PCBs and make as many of them as they want on their own. Or make alternative firmwares for it, or anything else like that.
Excellent. So this was Dimitri from Emute Lab Instruments. Have a nice Bristronica.
Thank you, you too.
Cheers.
Bye.